So today is our second and last lecture in Chapter 4, dealing with two-dimensional steady-state conduction. We were introduced to the finite difference equations. I emphasized the energy balance approach to get our equations. You're going to get n equations. N is like 20, 30, 50, 1,000. That's how many equations you'll have with n unknowns. And basically the unknowns are the temperatures for this class. It will be the temperatures at location 1, the temperature at location 2, the temperature all the way to location n. You solve for temperatures at locations, and that's a mesh. That's a finite difference approach. And then once you have it, you can answer questions and do some calculations, like what is the rate of heat transfer through this material, what's the efficiency, other things. So how do you set up and solve n equations and n unknowns? Usually linear algebra, big AX equal B, if that makes sense, where this is a big matrix A. This is a column vector of unknown quantities that you want to solve for, the x's. And what's B? The right-hand side. And so all of those temperatures are in it's like T1, T2, dot, 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 dot. AX equal B. You took numerical methods that covered it. You had engineering analysis that covered it, and you've probably seen it in other classes. In theory, you get the inverse of that matrix. And when you multiply A inverse on both sides of the equation, on the left side of both sides of the equation, this turns into the identity matrix, and so X is just simply A inverse B. The other thing I'm going to try and do is a little exposure to Excel. We don't use Excel in numerical methods, we use MATLAB. And so you probably have more experience with MATLAB. So we have a two-dimensional straight triangular fin of length L of 50 millimeters, and the base thickness is 20 millimeters. So it's infinitely long. So right away, delta Z or Z, we're just going to pick 1 meter, 1 something, and not worry about it. It's really in 2D. I'm not going to stress the 3D part of it because it's infinitely long. You have thermal conductivity of the material, and you have the base temperature. The base temperature is all specified right here, and it's exposed to a convecting fluid, and you have the convection coefficient given, and the temperature of the convecting fluid. Okay, with that finite difference mesh as shown, what do you mean? They've shown 21 nodes at different locations, right? What they want you to do is to solve for the fin efficiency for this triangular fin. How are you going to do that? Well, what you're going to do is you're going to solve for the temperatures at each of those nodes. And then once you have the temperatures at each of those nodes, you're going to get and compute the fin efficiency as the ratio of what is the actual heat transfer off of that fin compared to if it was a perfect fin all at the base temperature, Q max. All right. So let me stress that you're going to solve for all of these temperatures. Now that you're going to exploit symmetry, so right here is a cut it in half. They didn't put nodes down in the bottom half, did they? You don't need to. From symmetry, you exploit it, and you reduce the number of nodes. So think about this for a minute. I'm going to get the temperature at 6. Actually, I don't even need to do any work because that's a boundary condition. It's 50 degrees C. It's the base temperature, isn't it? Then we'll have the temperature at node 11, at 15, at whatever, 18, 20, and 21. So if somebody said calculate Q, this Q right there, you would say it's how much is coming off of the fin surface. And I'm just going to worry about that top half because of symmetry. I would double it. It would be for the full fin. And so it's like I have a certain amount of real estate up here devoted to node 6. I have a certain amount of real estate devoted to node 11. And then between 11 and 15, cut it, and from that part to the cut right here between 15 and 18 is real estate devoted to node 15, etc. So what we're doing is, you can see that, and with just a little bit of geometry or calculation, you can find this length. And I'm going to call that length DL. It's the separation distance between the midpoint and the midpoint, or you could also say between node like 15 and node 18 along that edge, that convective edge. With a little bit of work, you find that DL is equal to dx squared plus dy squared, where the spacing dx, x goes all the way out to 50 millimeters, right? But you have 1, 2, 3, 4, so you have 5 subdivisions, and so this delta x right there, dx, is going to be 50 divided by 5. Isn't it going to be 10 millimeter? So this will be the square root of 10 millimeters squared plus, and if it's y, and from it's 20 millimeters there, so it's 10 millimeters here, and I have 1, 2, 3, 4, 5 subdivisions, then dy is equal to 2 millimeters, isn't it? A little bit of work, 2 millimeters squared, and it comes in a little over 10 millimeters for DL, but at least we have it. It's a little bit larger than 10 millimeters, and that's the length of the edge for the convection for each of those nodes on the top. So Q is equal to H times, the first one for node 6 is DL divided by 2 times T6 minus T fluid infinity plus H times DL times T11 minus T infinity plus H times DL T, I don't need that parenthesis right there, T15 minus T infinity plus H times DL T18 minus T infinity plus H times DL T20 minus T infinity plus H times DL T21 minus T infinity. So that's how we would calculate numerator needed to calculate the fin efficiency. I have to solve for those temperatures. The ones that are really important are the ones along the convective top. Okay, what about this Q max? What is that? Well, you could take this previous equation and say the same. I made one mistake. Do you see my mistake? Yeah. I forgot to divide this one by 2, right? DL over 2. Right. Some students are just waiting for the instructor to write something wrong. But this is good. Thank you. How many people saw that? Good. You're awake. Right? Very good. So I'm going to probably do a few more of those before the end of the lecture, so pay attention. So anyway, it would be H times DL over 2, then you'd put T base minus T infinity, blah, 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 blah. And you just take this whole equation, and then instead of the individual temperatures, take the base temperature for the surface temperature. Somebody says, why don't you just do this? Why don't you just give me the total L there, which is, I can calculate. It's going to be a little over 50, right? It'll be, the total L here will be the square root of the 50 squared plus 10 squared. Okay, so you have H times this total length times the base temperature minus T infinity. You have the numerator, you calculate the denominator, and you calculate the fin efficiency. So it seems funny that the numerical solution can give you this metric for the overall performance of the fin efficiency. But really, deep down, all you're doing is using numerical methods to give you the surface temperatures. Okay, you ready now to solve the problem to get the temperatures? See where we're going? So here's a mesh. In the interest, I've made a photocopy handout, so I'm going to pause and pass that out for you. All right, so what I was asking you to do is discretize it. So basically, halfway between the sets of nodes, put in a dividing line, and likewise horizontal dividing line, and where they intersect are going to be the corners of the control volumes or control areas for each node. And so this one goes through like that. It goes all the way across and all the way across. It's hard to, I see some of you have straight edges, and that makes it very accurate. You know, if you draw it accurately, it's a lot better. And then this one goes down and down. Okay, so for example, if somebody said focus on node 9, that is the real estate or the volume associated with node 9. And node 9 has some neighbors. Node 9's neighbor is 3. Node 9's neighbor is 10. Node 9's neighbor is 14 and 8. And so thermally, we can have a pathway for conductive heat transfer between 3 and 9, 10 and 9, 14 and 9, and 8 and 9. Okay? Now, just a little bit here. We already worked this out. But the distance between node 1 and node 7, we worked that out to be dx, and dx was 10 millimeters. True? What is the distance between the line, the blue lines? Is that also the same value of dx, 10 millimeter? Yes. We're going to keep very simple meshes for this purpose. You know, just make it easy. Likewise, dy, we worked it out, and the dy is 2 millimeter, right? All right. So now the question is if we focus on node 9 right here, or any other interior, but I think it's easier to start with the interior. You only have conduction. Write the energy balance for that node. So the energy balance is going to be the sum of 4 conductive heat transfers into the node must equal to 0. So the first term, let's go from 3 to 9, would be a thermal conductivity of the material, an area to length ratio appropriate for node 3 to 9, times the temperature of node 3 minus the temperature of node 9. And then likewise, we'll have a K, A over L, for the conductive from 10 into 9. Whoops. From 10 into 9. We're going to have all of them assume transfer in. The computer code will take care of the negative signs. Plus K, A over L, from 14 into 9. And then the K, A over L, the temperature at node 8 minus temperature at node 9. The sum of those rates of heat transfer into the control volume for node 9 must equal to 0 at steady state. That's our energy balance equation. The hard part is what are those area to length ratios. So this is my clicker question for you. It could be that the area to length ratio would be delta y divided by delta x, or delta x divided by delta y, or delta y over 2 divided by delta x, or for D, delta x divided by 2 divided by delta y. You see your choices? So what we're going to do is we'll work on this one first, and we're going to work on the area to length ratio from node 3 into node 9. And so there you go. Well, I think what I did was, let me copy this. Edit, copy. I think I even blew it up. I blew it up. All right, because this is so confusing to a lot of people. And now we do an edit with the paste right there. So these are still our choices for the answer. And the question was, for the transfer of heat from node 3, right here, into 9, what is that? Is that my area? And this is my length? Is that what it is? So that when I do my area to length ratio for 3 to 9, this would be my area, and this would be my length. And what about the delta z? Well, this height times the delta z, so in the area term, I'm just letting that be 1, that delta z equal to 1. I'm leaving it out. So seeing it a little better like this, I want you to now re-answer the same question. What is my area to length ratio in terms of either A, B, C, or D answer from node 3 into node 9? All right, let's take a look at our results now. So, we're still not at unanimity, are we? But we have a high percent correct, right? So, isn't it this distance right here represents the area? I know we multiply that by delta z, but that is the height, delta y, that distance. And then the length is the delta x. So this is the correct answer, A. Let's see how we answered the same question. Well, okay. Now let's go back here. So we're going to fill this one in with delta y over delta x. Now, let's do 10 to 9. That's this one, from 10 to 9. What is the correct area to length ratio? Is it A, B, C, or D? Well, let's take a look at our results. Hey, that's pretty good, isn't it? Isn't the area this delta x and the distance L is delta y? So very good. So this one is delta x divided by delta y. And so only one person missed it. 14 to 9. What is my area to length ratio from node 14 into node 9? All right, let's see how we're doing. Oh, I'm a happy man. That's great. This was delta y divided by delta x. True? If you do it for node 9, it's very similar for node 8. And it's very similar for, let's say, node 14 and 13 and a lot of interior. But we have to start worrying about our convective edge nodes and do the energy balance for our convective edge nodes, okay? So what we're going to do is we're going to focus on node 15 right here. And we already calculated what DL is, so you can use that in the equation. And what's happening over here? Don't we have convection into this fluid? Yeah, and that fluid temperature is T infinity. Can you write an energy balance equation for node 15, and all of the rates of heat transfer, you write them as going into node 15, just like we did it going into node 9. How many conductive pathways do we have? And then we have the convective. All right, so when you're first new at this, go slow, but you're going to go from 10 into 15 and 14 into 15 and from the fluid into 15. Otherwise, you could have a sign error if you're not careful. So the sum of all of them must equal to 0, all the transfers in. So we're going to have T10 minus T15, and we're going to have a K, and then I have to really go slow on this. What is my area? What is my length? So my area is going to be a delta y, my length a delta x. And it is a full, it's a full delta y. Okay, and then we're going to have our T14 minus T15. That's the easy part. Put the K over here, slow down. What's my right area to length for conduction coming from the bottom? Delta x, distance, delta y. Then I put an h, then I'll put a t, what? T infinity minus T15. Everything's going in. Don't switch it. Don't now write T15 minus T infinity. All right, now I have this length, and all it is my dl that I worked so hard to get. Isn't it just dl? Nothing like dl over dx or anything? No, 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 just dl. As soon as you get that equation down, then move to node 21. Because node 21 is a little unique, isn't it? So how many conductive pathways into node 21? Only one, isn't it? Only one. See, 20 doesn't go into 21, only 19 into 21. So T19 minus T21 with the K, and then I have to get the right area divided by the length. At this point, what I'm going to do is I'm going to do an insert, paste, or paste, paste, paste. I still have my choices right there, don't I? Don't I?
Sure do.
Sure do. And what I'm going to do is I'm going to start that up. And what is my appropriate area to length ratio for the conductive transfer from node 19 into node 21? Okay, so I think if I would have given you more time, is it dy over 2? Because to go from the blue line to the node is only half of delta y. Maybe I should have zoomed in right in there, but I didn't. But it's delta y over 2, or dy, or I kind of go like both of those, dy or delta y, sorry. And then you divide by the distance, delta x. Maybe I should be consistent there. See? Do you see why it's divided by half?
No, I don't.
It's like, what is the distance between this blue line and that blue line? Is that a full delta y of 2 millimeter? And then say, what is it from the node down to the blue line? Half of it. Or from the node up to the blue line, half of it. And then we look, and what we have is we have the blue line to the symmetry line, which goes right through the node. It's not like the symmetry line is below the node. Yeah, the symmetry line goes right through 1, 7. So when I come over here, that distance from here, right here, is only dy over 2. See it?
Yes.
Oh, yes, I have to finish it out. Thank you. So now what we're going to have is we're going to have not a dl, but an hdl over 2 for the convective times the T infinity minus T21. The sum of those two is equal to 0 for the energy balance of node 21. Thank you for not letting me forget that. Does that look good? Now, there's only let's do one more. Let's do node 7. Do you want to do node 7? We can do it right here on this page. So this was the node 21. Do it for node 7. An energy balance for node 7. Paying attention to So let me kind of walk myself through it. So I'm going to have from T1 to T7 a conduction. I'll have a K, but here's my area delta y over 2 divided by delta x for 1 in the 7, right? Then we're going to have from 8 into 7. We'll have the K, and then I go slow right here. I'm thinking my area, a full delta x. My distance, a full delta y. Is it a full delta y? Yes, it is. It's confusing, isn't it? Or potentially confusing. And then the last one, we have the temperature at 12 minus the temperature at 7 equal to 0. And then we're going to have a K. And then we have the area, delta y over 2. That's a delta y. And then divided by delta x. Look good? Look good? Okay. Now that you have all of your equations, you can go into Excel. But how many people have used Excel? How many people? No, there's a few hands. And I give you this problem, and I want to have you solve it with the calculator or whatever means you have available to you, and then I'm going to show how to solve it in Excel. It's a little warm-up exercise. Okay? Somebody says, here's my quadratic equation. Find the roots. Find x1 and x2 where, you know, it's a quadratic equation where y is equal to 0. There's two places, two solutions to this equation where y is equal to 0. You already have it? Okay. Negative 4/3 and 2. How would you do this in Excel? Somebody says, how do you do it in Excel? Well, basically, I would put a label down in a cell, and then I'd put a value in it, and it would be my initial guess. Maybe my initial guess is -3, all right? And then I would have my function or my y function, and I would code that up. And my y function for this problem is going to be equal to 3 times, this is my guess of x, quantity squared, minus 2 times my value of x, minus 8. And didn't I accurately implement my equation? Let me blow this up a little bit if you can see that. So this is my equation implemented. Hopefully you can read that. And then I sit there and I say, I want to now solve this. So I'm going to go and I can use a tool under data. And it's hidden right in here. I don't know why I don't see it better. But goal seek. And how many people have used goal seek? Couple? Well, this is a very, very nice tool. So what it is you say, take the cell, this cell right here, set this cell, but I don't want to set that cell. I want to set this cell, y, to the value of 0 by iterating and changing the x cell. And then I hit OK, and if I have a decent guess close to it, you saw it iterate, it went to negative 1.333, which is one of the roots, isn't it? And so it drove it to 0. You say, well, that's not close enough to 0 for me. Okay, then take this whole thing and multiply by 1,000, a trick to make it really go to 0 for Excel, and then redo. Go up to data, go to goal seek. Goal seek says, take this cell right here. I want to drive it to 0 by changing that cell. And, okay, well, I got it closer to 0. But anyway, it's negative 1.3333. Isn't it our solution? Okay. So you can come over here. I'm just going to copy this and paste it over here. This is the same function, but it uses this cell right above it. But this time, I'm not going to have a guess close to that root. I'm going to start with the guess close to the other root. I'm going to start with the guess of 2.2. Well, a guess of 2.2 is closer to the other root. Let's do goal seek. So we come over here, we say goal seek, and we say, I want to drive that cell. That's correct. It's the right cell, otherwise I change it to the value of 0 by changing this one. Cross your fingers. You could watch it iterate. It drove it down to nearly 0, and it got our second root. So sometimes when you're using these iterative solvers, like it's a Newton-Raphson technique, your initial guess drives you to one solution. Your initial guess will drive you to another solution. Okay. Somebody else says, I was taking the exam, and the professor had us do this silly problem. He said, solve for x, where x is the root of this equation, satisfies this equation where 0.7 is equal to the hyperbolic tangent of x divided by x. Last time or before the other exam, I said, do it on your calculator and be prepared for the exam. True?
Yes.
Can you do this in Excel? Let's do it in Excel. It's not that hard. You would use the same tool. So I would come over here and let me just reuse this part. I'm just going to copy and paste right here. So I'm looking for an x. Maybe I think the initial guess is 1.2 or something. I'm just throwing out initial guess. But my function isn't this quadratic, is it? No, no, no. What it is it's a 0. Let's do it this way. Hyperbolic tangent of x divided by x. Okay. So I want that to be close to a value. Did I say 0.7? So I use the goal seek, and it says take that cell, which is whatever it is, D6, and make it to 0.70, drive it to 0.70 by changing this value of x, and you hit the return, and there's the solution. So that x makes this equation equal to 0.7. Somebody says, well, I don't want it equal to 0.7. I want it equal to 0.35. Just do it again. And goal seek 0.35. And by changing that cell, and away you go. So there you go. Well, it's close enough to 0.35. Excel's definition of closeness isn't usually... As an engineer, a lot of times we want 6 digits on our numeric answer, and we drive it to real zero. What you would do here is, if you wanted it to 0.35, I would rewrite this. I'd put this as negative 0.35, and now I'm driving it to 0. And then I say that's not close enough to 0, so I take in parentheses around that, and I multiply by 1,000. And then I can come back in and say, goal seek this, drive it down to 0 by changing that. And it gave me some more digits on accuracy. So hopefully that was helpful to you. But we need to solve now not just one equation, one unknown, multiple equations and multiple unknowns. You could do it with AX equal B, linear in Excel. Good luck. I've done it. I've shown it. Got a lot of videos you can look at. Or iteration. When you have multiple, you're not just changing one variable, you go to this guy up here, solver. How many people have used solver? Would encourage you to learn solver. It's a lifesaver at times, okay? Just like goal seek. Once you kind of get familiar with what it does, it's like, aha, now I found another way to use it to my advantage. But solver allows you to have to drive something to a minimum, a maximum, or to a particular value by changing more than one cell. One cell or 10 or 20 cells at the time. And so that's what we would do here. So in the interest of time, let me say cancel that, close. I can do this. I can come over here and show you how I set it up in Excel. Otherwise, I try to build these from scratch. But over here, I put in a bunch of inputs. So let me see if I can blow that up. So this is the K, the thermal conductivity with units. These are just helpful reminders, right? And these aren't dx. Is that millimeter anymore? No, that's now meter, isn't it? It's not. I changed it. That's meter. And this is now meter, right? Okay. dx, dy, dl, t infinity, blah, blah, blah. And what I also did to make the cells a little easier is I named it. I named the cell. Currently, this, let's say the cell that I click right here, that's D2. D for the column, 2 down for the row. If I come over here and I click right there, it's J1, but I've renamed it to be K underscore. So I have a name for it. Anytime I want to use it in the formula, I can just type. I don't have to type or click J1 as a cell to grab the value out of it. I just say it's K underscore, and it knows, oh, that's over in cell J1. It makes the equations a little more readable. This is a value of H, but it's also named right here, H underscore. So I have this one as, yeah. It's instead of using that call to the cell, it's naming. So let's say I had a value over here, 88, and that was my BB number. Okay, well, over here, if I wanted to call that cell, which is normally G2, I would just come up here and I would just type the name I wanted to give it. I would call it BB. And because it gets a little confusing, I like to add that underscore, because otherwise it's saying BB column, you know, way over there in left field, BB column. No, just that. That's a good name. You pull this down, here are all the names that I've, as a user, defined. Helps me figure things out, keeps track. Okay. Then what I've done over here in this part is I've kind of laid out the temperatures, not in a column, but I've laid them out kind of in the shape of my triangle, with the 50, 50, 50 values of temperature at the base, the nodes 1 through 6, and then they start popping off over in here. Now, I've played with it a little bit. Let me get rid of this. And these are values that are just in there, okay? But I don't know if there's a solution. So what I have down here is I have a very similar triangle shaped, but I've color-coded a little bit, and these are the results of the energy balance using the temperatures up here. So let's take a look at this equation. What does that equation look like? Well, it's making calls over in here to pick up the things like dx over dy and dy over dx and thermal conductivity k underscore, and it's picking up the two temperatures here like that. So if I scroll up a little bit, you can see that it's using these temperatures around the green in cell C3. All right, I can pick on this one. You can see it's using the ones above and to the side. It's just doing the energy balances. Way out here, this is the energy balance for that one. But it's also anywhere up here that uses the fluid T infinity node value. Okay, so I say I want all of these to be equal to 0. How do I drive every one of those to 0 at the same time as I'm changing all those temperatures? I'm glad you took a class in numerical methods. That's the big thing, linear algebra. You have a bunch of equations, bunch of unknowns. All these equations need to be satisfied at the same time by changing all of these unknowns. And so what I did was a little trick. I used sum product. Basically, probably look at this one, is like I want this to be 0, this to be 0. So I square each of them and add them up. And then I add them all up. So I have an L2 norm. It's the sum of all of those terms squared. And then if I drive that 1 to 0 by changing all of the temperatures, basically it forces everything to go to 0. So now I'm ready for solver. So I can come to solver and I say, okay, solver, I've got this one cell, and it's a little hard. This screen doesn't let me make it smaller. But you could kind of click and you see, isn't that the H, whatever number it is, 17 cell, 16 cell? And I want to drive it to a minimum. I can't get it to 0. I'm trying to minimize the error. So I'm trying to drive it to a minimum by changing. And then here you could see it highlights all the cells that are going to be changing. I'm changing all those unknown temperatures at the same time by trying to drive one metric to 0. Good luck, cross your fingers, hit solve. It's using a nonlinear solver, using a simplex method, using these other methods. I just usually go with this nonlinear solver. They have other constraints and other things in there. So it drives it, and that's pretty good. That's pretty close to 0. I played around with it. You can grab an initial guess and replay this. Let's go up here and just throw them in, because that's my initial guess. The sum is not close to 0. But that's not a bad initial guess. And we come up here to solver, and you would like to say, okay, there's a bunch of options if you want to explore them for this, that. I don't have time. But hit solve, and it didn't really do a very good job of driving it to 0. It's sensitive to the inputs, the initial guesses. All I know is that if I come over here, I can grab the actual solutions that I've worked before, solved this problem before. The other video, I solved this problem last year as well. When I plug in those solutions, look at that error. It's really driven to 0. So hopefully that was helpful. That's an introduction to Excel. And we're done for today. Thank you very much for your attention.